normalizing cosmology. So please set up the clock there. Low. So you have about 35 minutes. You can check the time, okay?
Okay. Okay, good morning, everyone. Thanks to Farinal, Diaguno, organizers. Well, I'm going to talk about a simple model I am suggesting to that explain the possible smallness. I'm going to talk about a simple model that may explain the possible smallness of the sterile neutrino and reconciliate with cosmology. Things is the following. When you think about the standard model, what comes to our mind is the following. What's the simple extension of the standard model? You have the idea when you see the standard model that right-hand neutrino is missing. Why not to put right-hand neutrino into the standard model? Because it's got more natural to have right-hand neutrino in the standard model. But the point is, what the role of the right-hand neutrino, and what mass? In principle, right-hand neutrino would be a singlet by the standard model. This means that you cannot control the right-hand neutrino because it doesn't interact with the part of the standard model. In this way, you cannot have any information about this neutrino. Right-hand neutrino, in this case, means that they are sterile neutrino. They do not interact with the gauge balls of the standard model. So a natural mass, a natural value for the mass of the right-hand neutrino is around that TV. Okay? I mean, this neutrino is, we expect that this neutrino be naturally heavy. Okay? Another role played by this neutrino is in the origin of the mass of the active neutrino. Right-hand neutrino can give an explanation to the smallness of the standard neutrino. But for this, right-hand neutrino has to be heavy. And what is happening? At the moment, we have a great challenge in particle physics that are the result of short baseline neutrinos. You have two experiments that say that may exist sterile neutrino with mass around EV scale. And this is not natural. It is natural that this neutrino be heavy, but at least two experiments is giving indication that this neutrino must be very light. And you have to understand this, because this is challenging. In the sense that theoretically it's not natural, it's not easy to generate light right-hand neutrino, and light right-hand neutrino is disfavored by cosmology. You have great tension when you assume that right-hand neutrino are light. So you have a challenge for the model building, because you need to build a model that explain the smallness of the right-hand neutrino or extraline neutrino and be in agreement with cosmology. That's the idea of the model I'm going to suggest here. But before, let's make a short review considering the SBL short baseline anomaly. You have two results, LSND, it means boon. Only, I'm not sure, but only these two experiments have result with great significance. The other results are constrained, okay? What's happening is that these two experiments give indicate that there must exist sterile neutrino with 6.0 significance. So you have to take this into account. This is a serious result. Another experiment reactor radiative. Some experiment confirm, is in agreement with LSND mini-bone, and other short baseline anomaly do not agree with this result. So there is a tension involved short baseline anomaly. And this is another problem that I will not go in details here. The indication of right-handed neutrino has LSND, the first result, short baseline indication. This experiment is running since the 90s, long time of running. And perhaps you are face a great challenge in particle physics, because these two experiments indicate this new particle, and if this is confirmed, it is necessary new confirmation. And if this happens, you are in face of great problems in particle physics. But I'm going to talk just about, I'm going to consider just LSND mini-boon, because these two experiments has really result with significance. LSND mini-boon has detected a kind of excess of electron and anti-electron neutrino, an excess. Okay? This is, in fact, what they are detecting. If you interpret this excess in terms of neutrino oscillation, there must exist a new neutrino with mass around EV, and with a robust mixing with the active neutrino. This is the problem. Practically, the problem is the mixing that must be very large. Okay? Well, what happens is LSND mini-boon generate a beam of proton. This proton hit a target. I don't know which compose this target. In the end, you have pile plus and pile minus. I don't know why, but pile minus is absorbed by the target, and in the end, you have pile plus. This particle decay in anti-muon and muon neutrino. And this muon decay in a positron and another neutrino. Right here. Okay, the pion plus decay, and see that in the end of the day, you do not have anti-electron neutrino. So this experiment is perfect to look for, to investigate oscillation among anti-muon neutrino and anti-electron neutrino. Okay? What they measure is the following. They measure an excess of anti-electron and electron neutrino with a very large mixing with this mass difference. This is the LSND result that was confirmed by the mini-boon result. Okay? And this is the LSND result, 2001, and this is the mini-boon result last year. Okay? You see that mini-boon confirmed is in agreement with LSND, and joint analysis suggests a significance of 6.0 sigma. So this is a discovery. Right? But unfortunately, you cannot say that really there must exist sterile neutrino, because those experiments may have alternative explanation. And there is a range of data that should be analyzed, and you cannot say, I don't know why completely, why these two experiments is not sufficient to say you have light hydrogen neutrino. In other words, you are in a hard situation because you have to expect, you have to wait for another experiment. And among the SBL experiment, there is a tension because another experiment do not confirm LSND because they are looking for disappearance of neutrino, and there is a tension among appearance and disappearance, excess and deficit. But you have a lot of experiments, and I think in a couple of years this will be solved, and you hope you have a final result, say exist or not. This is the question of disappearance in appearance. There is a possibility of have agreement among appearance and disappearance if people do not take into account a kind of low energy minimum data. But this is very controversial, and what I'm going to do from now on is to assume, I'm going to assume that yes, there exists sterile neutrino, largely mixing with the active neutrino and with mass and EV scale. And I'm going to propose a model to explain this. Well, there is this tension, a tension among appearance and disappearance. I think Pedro Machado must talk better about this. And when you assume that there is, in fact, EV neutrino, when we assume that there is light right-handed neutrino, you have a problem with cosmology. Cosmology doesn't accept light right-handed neutrino. So you have to escape from the cosmological constraint. And this is not easy. You have to make an extension of the standard model to evade such constraint. Ah, okay. 22. I got crazy. Okay. So let me EV sterile neutrino versus cosmology. Great problem here because cosmology, EV sterile neutrino is a new degree of freedom, is a relativist degree of freedom, and this is not compatible with the current measurement of the number of effective of relative degree of freedom, cosmic wave background, and large scale structure. Light sterile neutrino do not agree with the cosmological data. So you have a tension among EV sterile neutrino and cosmology. How to solve this? There are to solve this problem is very intriguing. It's very challenging. You cannot have light sterile neutrino in the beginning of the universe. The problem is in the beginning of the universe. Today, they can be light, no problem. So you have to evade this in the beginning of the universe. So one possible is, in the beginning of the universe, these particles are heavy. Because if they are heavy, you can say heavy or the mixing very small. You have to suppress the mixing in the beginning of the universe. After that, you can have large mixing. In other words, you need to you need that this neutrino be heavy or have a small mix before the before thermalization. They cannot thermalize in the early universe before the active neutrino decoupling. This is the problem. You have to avoid this. Another possibility is these neutrinos doesn't have mass in the beginning of the universe. Only after the decoupling, you can trigger a VIV, and you have a phase transition, and the mass of this particle appear after the decoupling of the active neutrino. So there are many possibilities to evade this constraint. What I'm going to assume here is the first one, the mixing of the sterile neutrino with active neutrino is suppressed in the beginning of the universe because I'm going to assume that there is a medium, and this particle is going to propagate in this medium, and this medium will suppress the mixing, and this will solve the problem. Okay. So I have to propose a model that explain the smallness of the sterile neutrino, and that suppress and evade the cosmological constraint. That is the challenge of the model I'm going to show here. In practical terms, what happens is the following. If the sterile neutrino fill a medium, what's going to happen is that propagation in matter. Wow. If this neutrino is propagating through matter, it will get fat, more or less. And this fat means that it is going to face a potential. This potential is generated by the temperature. And in face the potential, then you get mass. It's like you are running in the sea and running in the sand. If you are running in the sea, you get fat, much more effort to run into the water. But if you are in the sand, you are light. So this is the idea. There is a medium, and this medium makes that the sterile neutrino develop effective mass. And with temperature decreasing, this medium disappear, and today you can have light sterile neutrino with no problem. This is the idea of generate a medium to suppress the mixing. This is the mixing among sterile neutrino and active neutrino. How can you get this? The idea is that there must be a secret, what you call secret interaction. What is a secret interaction? Is an interaction, is a new particle, maybe a gauge boson, a vector boson, or a scalar, that interact only exclusively with sterile neutrino. So you need an extension of the standard model that generate small right-handed neutrino. This is very difficult, and have a very, very light, and have a particle that interact exclusively with sterile neutrino, and more. I didn't put it, but this particle must be very light, most lighter than the sterile neutrino, in sub-eV scale. So this is very challenging, right? But you can do that. The idea is, wow, I'm lost here. So if you succeed in do that, you are going to explain the smallness of the neutrino mass. involve active and sterile, and evade the cosmological constraint. The problem is the following. What is the origin of neutrino mass? You know that you expect to explain neutrino mass through this operator, effective dimension 5 operator. This operator, when this scalar develop with, you have this here. You have to realize this, you call this seesaw mechanism. You have to realize these things here, okay? You have to realize this mechanism. For example, if this is the weak scale, this V squared 10 to 5. If this is a gut scale, 10 to 14, you are going to have EV. So you may explain the smallness of active neutrino with a large scale, large energy scale. This is the essence of seesaw mechanism. Okay? How can you realize such effective operator? You can realize by many ways. The most popular one is the canonical type 1 seesaw mechanism. This is very well developed, and this is the way you realize the type 1 seesaw mechanism. You need a heavy right-hand neutrino with mass at gut scale, and this is the standard valve. Okay. So in the end of the day, this process here realize the seesaw mechanism. But in the type 1 seesaw mechanism, right-hand neutrino or sterile neutrino are very heavy at gut scale. This doesn't serve to explain SBL anomaly. The another possibility is type 2 seesaw mechanism. Type 2 seesaw mechanism require a scalar triplet. When the neutral component of this scalar triplet develop VEV, you have the seesaw mechanism. But in this case, again, this scalar triplet must have mass at gut scale, very heavy. Another possibility to realize that effective operator is through one loop radiative correction. In this case, it is necessary to expand the standard model with new scalar, and this new scalar can have mass at TV scale. There is another possibility through radiative correction, but now involving new charged leptons. And these realize the effective dimension 5 operator. And at TV scale, you can realize that effective operator through inverse seesaw mechanism. This is the inverse seesaw mechanism. And these new neutrinos here belong to the TV scale. An alternative inverse seesaw mechanism involve another right-hand sterile neutrino with mass at TV scale. So I don't know any mechanism that generate a light active neutrino with light right-hand neutrino. As far as I know, I don't remember to see a model try to explain light neutrinos with light neutrino. That's what I'm going to do. That's my challenge. That's the challenge. So the idea of the model is the following. If sterile neutrino is confirmed, you have to review the idea of seesaw mechanism. You cannot have seesaw mechanism with sterile neutrino with mass in the EV scale. How can you realize seesaw mechanisms? I don't know. Okay. Remember that right hand right right right-handed neutrino through seesaw mechanism give the heavy right-handed neutrino giving the origin of light active neutrino. So if right-handed neutrino are confirmed to be light, you have to change the paradigm of seesaw mechanism. In other words, I suggest that seesaw mechanism work in very low energy scale. Is that possible? Of course it's possible, because seesaw mechanism is that relation here. This is seesaw mechanism. What people do is the following. This is the electroic scale, and this is gut scale. Okay? So, but it is possible that this parameter here be small, for example, 10 to the 2 eV, and this another parameter here is small, 10 to 5 eV, but bigger than the MD. This realize the seesaw mechanism, okay? Because you have in the end sub eV neutrino. So my idea is to generate a model that realize seesaw mechanism at low energy scale. I don't know why people had not think about this. I think this is because of the LHC. People try to see right-handed neutrino with at least TV scale, because it can be probed at the LHC. But perhaps the SBL anomaly say no, these neutrinos are light too, and then you have to change the way you are thinking particle physics in neutrino with seesaw mechanism. So the model is the following: get the standard model, add right-handed neutrino or sterile neutrino, add a second scalar doublet and 2 scalar singlet, apply an appropriate Z3, Z2 symmetry in such a way to have this Yukawa interaction. The idea of this symmetry is to avoid that the standard doublet Higgs, the standard Higgs, didn't give mass to the sterile neutrino. If those have, you have to avoid this. So this is the reason to the second doublet, and the reason to Z2 symmetry and Z3 symmetry. You just need this, right? What the role of this second singlet? I will say soon. After the particle develop wave, we obtain what we want, that is the seesaw mechanism, okay? So this wave here, 10 to the 5, and this 10 to eV. What you need, this my proposal here is that this seesaw, this canonical seesaw mechanism be realized at a very low energy scale. The point is this possible? If you succeed in find a set of Yukawa coupling that generate the desired mass for the neutrino, you say yes, good. So, for example, if I get V2 10 eV, V5 10 5 eV, and these Yukawa couplings, when you solve this mass matrix, when you diagonalize this mass matrix, in the end of the day, you get this mass spectrum. So the first 3 mass are the active neutrino, and with that mass we express solar and atmospheric neutrino. Okay, and see this set of Yukawa coupling, this set of value for this parameter, give a 4th neutrino with mass in the eV scale, and other 2 light sterile neutrino. But this is sufficient to explain SLND and mini-Boone experiment. But you need the mixing. In order to diagonalize this mass matrix, the mixing matrix with this data is exactly this one. Observe that this 3-3 block is the UPMNS mixing matrix. This explains solar and atmospheric neutrino oscillation. And those are the values that you need to explain mini-Boone. For example, these two matrix elements can accommodate LSND in mini-Boone. So, in fact, you have a model that may accommodate LSND and with light sterile neutrino, largely mixing with the active neutrino. So, those are the elements you need to explain LSND mini-Boone. But the point now is cosmology. How can you generate a secret interaction? Remember that in the Yukawa interaction, you have this interaction here. This singlet, the pseudo-scalar of this singlet cannot mix with the another pseudo-scalar. If I succeed in doing this, I evade the cosmological constraint. For this, you go to the potential. When you develop the potential, this is the potential that obey all the symmetry of the model. So I need to go to the pseudo-scalar mass matrix. This is the pseudo-scalar mass matrix in this basis. I am looking to this particle here. Perceive that this particle here, it decoupled from the another scalar. So you have a secret interaction. You succeed in getting a secret interaction. And the secret interaction you have is this here. So there is a chance to evade the cosmological data. Okay? But the point is, this scalar should be very, very light. So this is, that's the mass term, the mass expression to that scalar. And the condition to evade the cosmological constraint is that this scalar be at sub-EV scale. As a result, you have a constraint on this parameter here. But what is that parameter? That parameter, if you return to the potential, is here. This term here violates explicitly lepton number. Remember that in the canonical seesaw mechanism, it is lepton number must be violated at very high energy scale. So here, according to this model, in order to evade the cosmological constraint, lepton number is being violated in very low energy scale. So this is completely different from the canonical seesaw mechanism. Okay? And the VIV is this value. In order to avoid the cosmological constraint, we need that this interaction, you need this interaction with a very, very, very light scalar and with a coupling very small, 10 to the minus 5. This comes from the cosmology. And perceive that in order to display the mass of the neutrino, you have 10 to the minus 5. Okay? So, in fact, this secret interaction is in agreement with the secret interaction necessary to evade the cosmological constraint on sterile neutrino. Okay, perceive also that you have a sterile neutrino with mass at keV scale. This neutrino may be warm dark matter, and this neutrino also interact with this pseudo scalar, and this is sufficient to or this interaction. If you assume that this neutrino is the dark matter of the universe, it interact with the secret interaction, and this alleviates the problem of large scale structure. Other effect, we have 4 real scalar, and observe that this viv is in the keV scale. So you are going to have a scalar with mass at keV scale, and this may be a contribution to the G minus 2 of the Moore. You are going to have a single charge scalar. This scalar may give contribution to this hair lepton decay, and the upper bound on this hair lepton decay, you put this constraint over the parameter of the model, or else. So sterile neutrino are a hypothetical particle. You cannot say they exist. They are a hypothetical particle, but LS and D mini-Bourne is pointing out that such neutrino may exist. If such experiments are confirmed, you have a very, very nice result, an impact result in particle physics that you require hard work to understand this new physics. But you have tensions, and this tension you are giving the first step to try to solve and understand. You have many experiments involving this subject, a very exciting branch of particle physics, and thanks for the audience.
Any questions?
Hi, Carlos. Thank you for the talk. About the second singlet, do you have an estimative for the mass of the singlet?
Well, the second singlet, I didn't talk about it. The second singlet, what the role of the second singlet is, if you do not